Good morning, afternoon, or evening. Welcome to the talk for the paper titled PathCAS, an efficient middle ground for concurrent search data structures. My name's Trevor Brown, and this is joint work with my student William Seguin and Dan Alistar. Suppose you want to design a fast data structure for large multi-core systems, so maybe something like a binary search tree or a B tree, something that is very fast and can scale to potentially hundreds of cores. Well, there's a diverse spectrum of well-understood techniques that you could use for this task. You could start with an easy general technique like a universal construction, which takes a sequential data structure as input and outputs a concurrent one, but those tend to be slow. You could use transactional memory to achieve higher performance while keeping the implementation relatively simple, but hardware transactional memory is increasingly being disabled due to security concerns on modern architectures, and it's also not available on all architectures. For example, there's no implementation on AMD. You could use software transactional memory, but such implementations tend to be slow compared to handcrafted data structures. At the most difficult end of the spectrum you have, well, handcrafted data structures, which encompass both fine-grained locking ones and lock-free ones. And lock-free ones are probably so complicated that you don't want to pursue a fully lock-free approach. To make your job slightly easier, you might try using locks. And if you've never used locks before, you might think, like I did years ago, that a straightforward hand-over-hand locking implementation of a data structure would give you at least tolerable performance. In fact, if we compare hand-over-hand locking with a single global lock that protects the entire data structure and kills all concurrency, the difference is almost negligible, especially at high thread counts. So how are you supposed to get high performance if you're using locks? Well, the problem here is that any locking discipline that involves acquiring locks while you're traversing a data structure will effectively turn reads into writes, and this creates a huge number of cache misses because locking a node causes cache invalidations and evictions, and if we could do this search without locking, we could get something on the order of 100x speedup. So you better not lock during searches. And you can get some highly efficient data structures by combining locking updates with lock-free searches, or almost lock-free searches. The thing is, designing such data structures is difficult, maybe even as difficult as designing some full-blown lock-free data structures. Okay, so let's see an example. Suppose we want to design a lock-based doubly linked list, but we want to have lock-free searches. To delete E in this list, we might lock B, E, and H, and then change B and H to point to each other instead of pointing to E. At a quick glance, you might think that locking all these nodes before we change them is enough to make our update atomic. However, if we want to have lock-free searches, then our searches should be able to ignore these locks and flow through the locked nodes, continuing on their way to their destinations. Now, if searches ignore locks, then the locks do not make updates appear to be atomic from the perspective of searches. Rather, searches will be able to see the individual steps of updates. And this sort of reasoning mistake, thinking that you will get atomicity if you use locks, is easier to make than you might think, and it has led to subtle bugs in published algorithms. That was one of the motivations for this work in the first place, actually. My student, William Seguin, who co-authored this paper with me, discovered a bug in a lock-based tree whose nodes are also stored in a doubly linked list. Lock-free searches were allowed to flow through the data structure regardless of whether locks were held, and the idea was if a search ended up at the wrong place in the tree because it read some inconsistent data, then it should be able to use the next and previous pointers of the doubly linked list to find its way back to the correct node. Now, I won't go into the details, but Williams showed that it was possible to return non-linearizable search results if several threads perform operations that are interleaved in a specific way. Incidentally, the same bug was independently discovered by another group from the Technion, and the fix to the data structure is quite easy. You just flip 2 lines of code. So even locks are difficult to use if we want to achieve high performance. To make this task more reasonable, perhaps we should be using some sort of abstraction that's higher level than atomic instructions or locks, but still lower level than transactional memory, so we can really fine-tune the balance between expressiveness and performance. And to this end, there's a long line of research introducing multi-word synchronization primitives that can be implemented from atomic instructions and then used as a black box. For example, back in 2013, I actually introduced LLX and SCX, which are node-based generalizations of the load, link, and store conditional atomic instructions. Intuitively, you can use LLX to load a sequence of data structure nodes and then use SCX to atomically change one pointer and mark a subset of the nodes as deleted. And this SCX will succeed only if none of the nodes have changed since we read them. Now, you can implement some cool data structures this way, but of course the obvious drawback of SCX is that you can't change multiple pointers atomically. If you want to do that, then you have to use something like multi-word compare and swap, or as I'll call it in this talk, k-word compare and swap, or KCAS. So a KCAS takes k addresses as arguments, along with expected values for all of those addresses and new values for them, and it atomically does all of the following. If all of the addresses contain their expected values, change them all to their new values and return true. Otherwise, don't change any of them and return false. And in many implementations of KCAS, you have a KCAS read function that you have to use to read addresses that can be modified by KCAS. You can't read them directly. Okay, so at first glance, KCAS looks like a panacea, really a perfect solution. It can change multiple pointers atomically, and it can verify that multiple addresses contain specific values, so it should be easy to perform any sort of update that you want to atomically, right? Well, suppose we want to implement an internal binary search tree, and as a brief refresher, this is just the typical binary search tree algorithm taught in undergrad curricula all over. Inserting is easy. You just create a new leaf and link it in at the appropriate place in the tree. Deleting a leaf is also easy. It's just the inverse of inserting. Deleting a node with one child is easy. You just change a pointer in the parent to bypass the node and point directly to the child. And it's deleting nodes with two children that's the hard case here. So suppose we want to delete 6. To do this, we find the predecessor of 6, which is the largest key in the left subtree of 6, and then we steal that predecessor p's key and replace the key we're trying to delete with that, and then we've reduced the problem here to the problem of deleting that predecessor node, which now contains a duplicate key, and that node is going to be either a leaf or a node with one child, so we've reduced this problem to one of the previous two cases. Okay, so what if we want to implement that tree in a concurrent setting using KCAS? Well, it turns out that's a surprisingly difficult task, even if we have KCAS. To see why, suppose we start doing an insertion of key 37. Of course, it starts at the root node, which contains 40, and then since 37 is smaller than 40, it goes down to the left. And suppose that insert of 37 goes to sleep for a moment, and then a delete of 40 atomically completes. So the delete begins. It's a two-child delete, so it needs to find the predecessor, which happens to be 37. It'll replace the key 40 with the key of the predecessor, and it'll unlink the predecessor node. And now that this delete is completed, suppose the insert of 37 resumes. It'll continue its search down to a leaf. It'll conclude, because it hasn't seen 37, that 37 isn't in the tree, and it'll insert 37 into the tree. But this is a duplicate, and this is supposed to be a set that's being shown here, not a multi-set. So there should be no duplicate keys. This is a problem. Okay, the problem here is that in data structures where you first search for a location and then perform a modification, KCAS only helps you after you've completed your search. In other words, KCAS makes the modification phase atomic, but it doesn't make the search phase atomic. And the atomicity of your modification doesn't actually help you if a search takes you to the wrong place in the data structure. In the end, you're still on your own to solve the problem of performing correct lock-free searches. Okay, can we use KCAS to solve this problem? Well, we can with kind of a brute force application of KCAS by including all of the addresses that are read during the search in the KCAS that we perform at the end. But we don't want to change all those addresses, so we just specify the values that we read from those addresses as both the expected and new values in the KCAS. And with this brute force approach, the KCAS will only succeed if none of the addresses that it read have changed since they were read. And so the whole KCAS will be atomic, and the entire search will be atomic with the update. However, because of the way that KCAS is usually implemented, doing this would effectively turn all of the reads done in a search into writes, and I'll explain a little bit more about that later. This will introduce huge overhead and contention near the root. Briefly, to see how this fixes the problem, that's if a deletes node deletes key 40 here by copying the predecessor key up and disconnecting the predecessor, the insert of 37, which includes everything it read in its KCAS, will see that the key of the root that it read has changed, and so the KCAS will fail. Now, this brute force usage of KCAS would be much faster if KCAS allowed you to compare only and not change some addresses. And this is exactly what multi-compare, multi-swap MCMS does. It gives you the ability to specify that some addresses in a KCAS should only be compared. Now, this sounds perfect for what we're trying to do. The problem is that the implementation of MCMS depends on hardware transactional memory to achieve good performance, and we've already argued that hardware transactional memory is not available all the time, and when it's not available, the implementation of MCMS is actually identical to KCAS and has the same pitfalls. And as we'll see a little bit later, even when you have hardware transactional memory, it doesn't perform as well as you might think it would. So now we can finally frame our contribution, PathCAS. PathCAS is inspired by the literature on multi-word synchronization primitives and also transactional memory. We designed PathCAS primarily for node-based data structures, although we can play fast and loose with what constitutes a node, so you don't necessarily have to be working on a data structure that's comprised of nodes. And it's somewhat similar to MCMS in the sense that we want to allow some addresses to be compared only, or in our terminology, validated. The interface is syntactically a bit closer to transactional memory than it is to KCAS or MCMS, meaning instead of making a single monolithic KCAS call, you're going to make several calls that build up arguments over time. In particular, at the start of a data structure operation, you invoke start. You can think of this as preparing a hidden object that'll accumulate all the arguments you're incrementally building up. And add should be called on any address that you'd like to change from a specific expected value to a new value. Visit should be called on nodes that you would like to validate. Well, what does that mean? Well, validate can be called to verify that no visited nodes have changed since they were visited. Exec is essentially just KCAS. It doesn't do any validation and it ignores all of the visited nodes. It just does a KCAS on the added addresses. The special sauce here is really in vexec, which atomically does a KCAS only if validation succeeds. So the validation and the KCAS are done together atomically. And there's also a read function for addresses that are modified by PathCAS. You can't read addresses that are modified by PathCAS directly. You have to read them through a function, just like you do with KCAS or MCMS. But these calls are actually automated in C++ using operator overloading. Okay, so let's talk about how PathCAS is implemented. Well, our implementation builds on the lock-free KCAS algorithm of Harris, Fraser, and Pratt, so let me sketch that at a high level briefly. So the way this KCAS algorithm works is, when you first make a KCAS call, all of the arguments to the KCAS call are stored in a KCAS descriptor, and then all of the addresses that are to be modified are sort of locked using like a lock-free locking technique. Basically, this entails taking all of these addresses and changing them from their old values to point to this descriptor. So all of those addresses become pointers to the descriptor, and at that point, we consider all of them to be locked for this KCAS. And if another thread comes along and wants to access one of these fields, it'll follow the pointer to the KCAS descriptor and help this KCAS operation complete. That's how we achieve lock freedom in that algorithm. And if all the addresses are locked successfully, the status will become succeeded, and they'll all be changed from the pointer to the KCAS descriptor to their new values. And of course, if any of them aren't locked properly because some value doesn't match the expected value, they would be changed back to their old values instead. Okay, so I'm skipping a lot of details, but at a high level, that's the Harris-Fraser-Pratt algorithm. How do we change this for PathCAS? Here's just sort of a high-level sketch of a few changes we made. To efficiently track changes to visited nodes so we can validate quickly, we augment each node with a version number. Whenever PathCAS modifies a node, it should also increment the version number of that node. And we decided to make the programmer responsible for doing those version number increments so that we don't have to bake a hard requirement into PathCAS that you're always operating on nodes which have version numbers. We'd like you to be able to modify arbitrary addresses with PathCAS. And it also would have made it less efficient. Having you manage it directly doesn't add too much burden to the programming effort, but it makes things more efficient. Okay, so how does the algorithm work? Well, all of these version number increments are going to become part of the PathCAS descriptor, and the programmer is going to make add calls in order to perform these version number increments. And you're going to do the same thing as in the PathCAS algorithm. All the addresses that we want to modify, including the version numbers, are all going to be changed to point to the PathCAS descriptor. And at this point, validation is going to occur. So the PathCAS descriptor also contains some collection of visited nodes and versions that those nodes had when they were visited. And by rereading the versions of these visited nodes, we can figure out whether they've changed in the meantime. If none of them have changed, then the status becomes succeeded, and we change all of these pointers to the new values. Otherwise, if we failed validation or failed to lock any of these fields, we'd roll back to the old values. Okay, so obviously I'm glossing over details. If you're interested in getting a deeper understanding, I welcome you to take a look at the paper for those details. That's the implementation. How can we use PathCAS? Let's see an example of using PathCAS to design an internal BST-based set with operations to check whether the set contains a key, to insert a key that does not already exist into the set, or to delete a key from the set. Okay, so how do we implement this? Well, we give each node a version number and also a marked bit that's set when the node is deleted. So a marked bit is a node that's marked is going to be precisely a node that has been deleted. And I omitted this detail earlier, but since marking is so common in concurrent data structures, our PathCAS implementation actually reserves the least significant bit of the version number to serve as the marked bit. That way, validation can efficiently check whether any nodes are marked at the same time as it checks that their version numbers have not changed. The result is that a marked node will cause validation to fail, which is exactly what we'd like marking to accomplish, because a marked node is a deleted node. Contains, insert, and delete operations will all call a search helper function, which is almost just a regular sequential binary search tree search, except it also calls start at the beginning and calls visit on each node that it encounters. And then it returns pointers to the final node that it finds, which will call the target node and its parent, and their versions at the time that they were visited. So let's see how this works. To insert a new key, 7 in this case, we'll first call search, which will return a pointer to the target node where 7 should be inserted, and the parent and their versions. Then we'll create a new leaf containing the new key, and we'll call add to specify that PathCAS should change the left pointer of the target node from null to link in the new node. And then since we're changing target, we should also have an add call to increment the version number, and then we'll call vexec to actually effect this change only if no addresses that we read, the entire search path is unchanged since we read those addresses. And if any of those addresses have changed, the vexec will fail, and then because everything's atomic, we haven't made any changes to the data structure in that case, so we can just retry from scratch. If the key already exists when we try to insert, then we'll see that 8 is already in the target, and we'll call validate to ensure that our search is atomic. And if validate succeeds, of course, the entire search path contains all the same values as they did when we read all those nodes independently. Incidentally, that validate call can be optimized away. See the paper for details. And I don't want to explain all the deletion cases, just one of them very quickly, the hardest one. If we want to delete a node with 2 children, so 6 in this case, we'll first search for 6, which gives us pointers to the parent and the target and their versions. And then we'll have to find the predecessor. So there's a function find predecessor that gives you the predecessor and the parent of the predecessor. And this works the same way as search. It calls visit on each node that it encounters. And we're going to use add to change the target key to this predecessor key and increment the version number of the target node, and to unlink pred by changing pred parent and incrementing the version of pred parent. And then finally, because pred is being removed and we mark nodes that are being removed, we mark it and call vexec to accomplish all of these updates and both searches, the search and the find predecessor search, all of that atomically in one shot. If vexec fails because we encountered contention, we just restart our delete from scratch. Okay, so, well, validating the entire search path sounds pretty naive. How fast can this approach really be? Let's see some performance results from 2 systems. The first one is a 256-thread AMD system that does not support hardware TM because it's AMD. That doesn't support hardware transactional memory. And we also have a 192 thread Intel machine that does support hardware transactional memory. And the experiment we're going to run is to compare a PathCAS based AVL tree. So that's a balanced tree. So it's not exactly what I just showed you, but it's essentially the same thing I just showed you with the same principles applied to add rebalancing operations besides, just insert and delete. And we're going to compare this PathCAS AVL tree to really the state-of-the-art in balanced BSTs as well as to some transactional memory implementations. And it's the usual sort of data structure experiment you might expect. You have a bunch of threads that are all accessing the same tree. They're accessing uniform random keys, and they're timed trials where they try to do as many operations as they can in a fixed time. So here's a graph showing our performance versus transactional memory algorithms. So these are AVL trees implemented using transactional memory. The workload here is 90% search operations, 5% insert, 5% delete, and the trees have 1 million keys each. On the y-axis, you have operations per second in hundreds of millions, so up is good, and you have concurrent threads on the x-axis. Okay, so here's the PathCAS AVL tree. Here's the PathCAS AVL tree with hardware transactional memory optimization enabled. So I didn't mention this before, but we can take advantage of hardware TM if it's available to get a small performance bump, but we really optimized for the no hardware TM case. This is transactional lock elision, which is a relatively simple way of using hardware TM that tends to be quite efficient when it does work. So it either has almost no performance or quite good performance. In this case, it has quite good performance, but we're still beating it by a wide margin, and the other transactional memory algorithms don't do particularly well. And we have some hybrid ones that use hardware and software transactions and some software transactions here. Really, transactional memory is not a serious contender for PathCAS, considering the small amount of extra effort that you need to apply to use PathCAS versus transactional memory. Well, how about versus handcrafted algorithms? In this case, we're looking at the AMD machine. And the workload here is almost the same, but we have 10 million key trees instead of 1 million. There's no real reason for that other than just showing you some other experiments. We also perform very well in the 1 million case for the corresponding graph here. So here is the PathCAS AVL tree. This one that's faster than us is the optimistic concurrency control-based AVL tree of Bronson and others. This really represents the state of the art in binary search trees for search-heavy workloads. We also compared with a bunch of other handcrafted algorithms, most of which I'm not showing here because they weren't as fast as Bronson. I want to highlight a couple of other algorithms here. There's the chromatic tree, which is implemented using LLX and SCX, and it's a pretty sensible competitor to pit PathCAS up against because both of these are techniques which attempt to strike a balance between expressiveness and ease of use and performance. LLX and SCX is, of course, one of the other multi-word synchronization primitives that I described earlier in the talk. So we do quite a bit better than that other approach, and I think we're actually easier to use and easier to prove correct than that approach. And we also have some other software transactional memory-based approaches which can run because even though we don't have hardware TM, these just use software. Okay, so we're a little bit slower than OCC AVL, but pretty good considering this warranted publishing a whole paper for a very complex algorithm, and this is a relatively simple technique. And you might wonder where we do poorly. So this is our worst workload, 100% update operations, and we're a little bit slower than the OCC AVL tree. Maybe we're not in the same room, but we're in the same building, whereas LX and SCX is halfway across town, and NoRec is on Mars. Okay, you might wonder how we do versus multi-compare, multi-swap. Very briefly, we implemented an unbalanced binary search tree using PathCAS, multi-compare, multi-swap with hardware transactional memory support and without hardware transactional memory support. And here are some results in millions of operations per second. And the punchline is that PathCAS is a couple of orders of magnitude faster. I don't have time in this talk to explain why that's the case, but you can find our analysis in the paper. And so to conclude, PathCAS adds efficient validation to KCAS to solve the problem not only of atomic updates but also atomic searches. And the simple approach that I showed here in this talk is surprisingly effective. We've used it to also implement a whole host of other PathCAS-based data structures. But I want to make the point that more subtle usages, apart from just visiting every single node in the search path and then synchronizing on everything, you can do more subtle things with this. This is really a synchronization primitive, not just a blunt methodology. And so you can find more creative ways of using these primitives, I hope, as well. There's a bunch of really important stuff that I didn't have time to get to in this talk, so I welcome you to look at the paper for those details. And with that, I'll conclude, and thank you for your time and attention.